some problems trying to get a hex keypad working with my 6502 breadboard computer, so I've taken a step back, I've disconnected it completely, and I've just wired it up completely separately just with some LEDs just to check that the encoder chip is working. And I think it is, because what I've done is on the 4 data lines I've wired up 4 green LEDs, and on the data available pin I've put a red one, and that's the one that I think we could use to trigger an interrupt when we connect it up to the 6522 versatile interface adapter. So let's see if it works. If I push a button, press button 1, you can see that the data available lights up when I press it. That's good. I can use that to trigger an interrupt. And when I press different keys on the hex keypad, you'll see different combinations of the 4 green kind of data lines light up. So we can use those then. We can connect those to 4 inputs on the 6522 versatile interface adapter. Read those hopefully and work out which button it is I pressed. So I know at least this bit of the circuit's working. The problems I've had getting it to work with the rest of the 6502 breadboard computer must be down to my software, so I need to have a bit of a rethink, but it's really good to know that at least this bit's working. So having done a bit of hardware debugging of my encoder chip for my hex keypad, I've done some more work on the program that makes it work. The idea is to make a computer that's a little bit like a KIM1 or an Acorn System 1. So this is a 6502 based computer that you're going to program by entering numbers on a hexadecimal keypad. The instructions will appear on the display, and you'll be able to run very simple machine code programs on a self-contained computer, so you won't need to connect it to any other computer. It won't have a display on it, it won't have a VDU. It's certainly not going to run BASIC. I'm trying to write my own monitor program to work a little bit like one of those early single board 6502 computers. I've managed to sort of get this to work now. I've got some challenges ahead, which I'll talk about in a moment, but basically what I've got here is I've got a hexadecimal keypad that is wired up to a little chip in there, which is very difficult to see. It's a 74C922 keypad encoder chip. What this does, it will encode a 4x4 matrix keypad, 16 key keypad, and send signals out, data signals out on a little data bus using 4 bits, and encode each digit that you press, or each key you press on the keypad as a 4-digit binary number, which I've now connected up to some of the inputs on the VIA, the versatile interface adapter. It also sends out, when you push a key, it sends out a signal, which I had on the red LED here, that data is available, and that's how the computer knows that I've pressed a key, and that is hooked up to one of the interrupts on the computer. So the computer says, hey, I know you pressed a key, I'm going to do something about it. Here's how far I've got so far. So I've got my computer powered on. It displays the name of the computer, the Micron 1, when you power it up. That's kind of like my little splash screen. And now when I press different keys, you should see over here text appearing. So I've managed to get it so that the interrupt works, and you see as I press a key, you might see the red LED over here lighting up, and different keys, when they're pressed, the data goes out on the data bus, the green LEDs here, and they're read by the program. We'll have a look how that works in a moment. Now, this is all well and good because I can use star and hash as E and F, and I've got a hex keypad so I can enter opcodes from my program. I do have a bit of a problem though. I'm going to need at least 4 more buttons. Now, there is a version of this chip, which is obviously the encoder chip, the 74C922, that will do larger keypads, but that's not the one I got, unfortunately. I bought the one that only does 16 keys, which is a shame, but that's what I've got. I'm going to have to try and work around that somehow. There's a couple of things I could do. There is a way of sort of daisy chaining another 4x4 keypad on top of this, but I'm going to need at least 1 more input, whatever solution I come up with. And I've used up all the interface pins on the VIA now. This is a very strict Ben Eater style computer. It might not look as tidy as Ben Eater's, but the and the layout is a bit different. But basically, the schematic of this part of the computer here is identical to Ben Eater's 6502 computer. Where I've diverged is adding this hex keypad, and I've only got 4 spare pins, I/O pins on the 6522, which is enough to do a hex keypad, but not enough to do all the other features I'm going to need to write a monitor program. I at the very least think I need something to step forwards and backwards through a program, I need a go button to start executing a program, and I need a stop button to stop it if it gets stuck in an infinite loop, so I can stop a program running without turning the power off and losing all my code. It'd be quite nice to do that. So how am I going to wire up 4 more keys? Interesting. Yeah, a couple of ways I could do it. As I said, I could add another keypad, requires another input. I could add a shift key of some sort, that requires another input. I don't have any spare inputs. So what I'm thinking at the moment, it's looking like I might have to change the way that the LCD is wired up. At the moment, it's running in 8-bit modes. So 8 of the pins are being used to address the LCD display, which is a little bit wasteful. These LCD displays can run in a 4-bit mode, although it's going to be a lot more complicated in software, but I'm thinking that's probably the path I'm going to have to go down. So my next step is probably going to be to rewrite the code to see if I can get it to work with the LCD display being driven in 4-bit mode, saving up, freeing up 4 more pins, which probably will be enough, I think easily be enough, to enable the functionality that I need with 4 more buttons to make a working monitor program. So here is the pinout for the encoder chip, the 94C922 encoder chip. And what you do basically to this is 4 of the inputs you connect rows on the keypad up to. So they're connected to pins 1, 2, 3 and 4. They're connected to the rows on my keypad. And the columns are connected rather strangely, but anyway, that's the way they go, to pins 7, 8, 10 and 11. So I've wired those up. Pin 5 goes to ground via a 0.1 microfarad capacitor. Pin 6 has something to do with key bouncing, debouncing the key presses. That goes to ground via a 1 microfarad capacitor. Pin 9 goes to ground. I've already talked about the columns. Pin 12 is the data available pin. That's the one that actually makes the interrupt happen, the one that I had connected up to my red LED. That's really important because when you press any key, and as long as you hold any key down, that will go high, and as soon as you let go, it will go low. So that's really, really important to let the computer know that you've done something, that you've actually pressed a key. Output enable is just tied to ground to make the thing work, and then the really important bit here is we've got 4 pins where the data comes out. This is where your 4 binary digit encoded number comes out on A, B, C and D, and they're connected to the versatile interface adapter inputs A0 through to 3. So that's all well and good. That's how the wiring goes. Let's have a look quickly at how the 6502 assembly language program works. This is very much based on Ben Eater's projects, including the one where he puts a counter in, but I never did the counter, so I don't have the counter variable sort of incrementing when you push a button. I didn't do that. But everything else is pretty similar. So it's got the same memory map. I've used the same abbreviations for different memory addresses on the VIA. So this should be very familiar to anyone who's got a Ben Eater program. Some things that I have changed. I found this helps a lot. Right at the beginning of the program, I turn the interrupts off and then do some setup. Setting some flags, set the stack pointer, setting some of my counters back to 0, clearing decimal mode, clearing the carry bit, just a bit of tidying up, a bit of housekeeping before the program starts running, and setting up the VIA configuration. One thing I've changed here is we have now got, instead of negative active edge, I've got positive active edge because the interrupt flag coming out of the encoder chip is going to go high when I push a button. So that's what I want to detect. Whereas with Ben's example with a push button, he had it going low. I want to go high. So that's why I've changed this instruction here that I load into the PCR, which is the peripheral control register. Instead of being 0, that's now 1. So that it reacts to a positive edge. So that's a big change. As I say, turning the interrupts off is new. Ben hasn't done that. I found this made a huge difference. So I turn the interrupts off, do all my setup, set up the LCD display, get all that working, and then I turn the interrupts on, and that's made a big difference. Things seem to be working an awful lot better. I then have a bit of code here that just prints the splash screen. That's the Micron 1 text down at the bottom of the screen. So that's what this does here. and then I send an instruction to put the LCD cursor back at the home position. Now in the main program loop, this is the part of my monitor program that I'd already written where I can step through memory and read the contents of different memory addresses, and also print an ASCII character, the ASCII value of each memory address, on the display. Just to test the keypad and get it working, I've commented all of this out. So this code does work, but I've commented it out just so I can practice typing. I've got a couple of strings here in memory, places in memory where I'm holding some ASCII data. So the splash screen is all got lots of leading zeros because I want it to wrap onto the second line, and then the name of the computer goes here. And then this is quite important. This string here is called keys, and that is where I keep a list of all the key presses in order. Now the order is a bit arbitrary. This is just as a sort of function of how I wired up my keypad. Because I wired up the keypad in this particular way, that's kind of how it's come out. You could rewire it so that the keys are in a more sensible order, but I couldn't really see the point. I thought it was easier just to do it in software. So basically what I've got here, when I add my keypad to the decoder chip, each key here is listed here. This is the binary pattern that it presents on the data bus on A, B, C and D when you push each key. As you see, the order is a little bit arbitrary. This column here shows you the decimal value of each key press, and this basically tells you the position in that string of that key. So let's have a look at the first character. Then 0 is going to be 1, so that should be the first character in my string. The next one is going to be 7, and because that's got the value 1, and the next one is going to be 4, so it should go 174 in my string. Let's have a look at the code for that, and there we go. 174 are indeed the first 3 characters in my string. So these routines here, these subroutines are all copied from Benita. These are all subroutines to make the LCD display work. Waiting for the busy flag to be cleared on the LCD display so you can write to it. And another subroutine for sending instructions and printing characters. They're all exactly as per Benita. So we can ignore all of those for now and then look at what do I do here. IRQ is what happens when an interrupt is received by the processor. This is the code that it's going to run. So the first thing it does is it reads port A on the versatile interface adapter. Now I'm only using 4 pins for this purpose. The rest of the pins in there are used for controlling the LCD display. I've connected the key encoder to these bits here on port A, the sort of least significant nibble of port A. So I'm going to AND what I've read from port A with that, with just 000111111. So I'm only looking at the least significant kind of nibble. So I've loaded that into the accumulator. I've stripped out any of the bits that I'm not interested in. And then I transfer that into the X register. And that's really clever because what we do here now is I can use the X register as an offset to work out which character position I've got in that string up here, where I've got all my characters in order, in numerical order for the sort of nibble that comes in from the keypad encoder. So it will use that to offset, to kind of slice that string and send the right character out to the print character routine. That's all it does, and it then returns from the subroutine. So it's really, really simple. So it does seem to work. It's quite a nice little program. It shows me proof of concept that I can read a hexadecimal keypad on my 6502 breadboard computer, and I can print the right characters on the display. So that's a good step forward to making my monitor program. But as I say, I think I've run out of pins. I need to do another double check. Looking around now. Need to do another check. Actually, I've got a feeling now. I wonder whether I have actually got one spare pin, whether I can do something cunning to wire up some sort of shift key to add some more buttons to make a working monitor program. But anyway, that's for another day.